This video is about partial fraction decomposition. It's the last video in our series. It's just a bunch of notes and reminders that might be necessary as you go through your homework. So just a note, back in algebra class you probably solved problems like this. You may have been given a rational function and a rational function and just asked to subtract them. And so you got a common denominator by multiplying by just the right thing here and here. You multiplied by well-chosen ones, you distributed, and then you got a common denominator and you brought those together. Partial fraction decomposition is just doing that in reverse. You're saying, I'm going to start here and I want to write this in this way. What are the values of a and b? I'm saying this is equal to this. What are the values of a and b that make this equal to this? And we talked about how to find a and b. As you're doing these problems, you've got a rational function. Don't forget to try basic rules and use substitution first. If you can use basic rules or use substitution, that's going to get you closer to the answer. So do that. It's going to be easier for you than partial fraction decomposition would be. So keep that in mind. Also, if the degree of the numerator is greater than or equal to the degree of the denominator, you want to use long division first. So maybe you've got a problem that looks like this. Well, the degree of the numerator is greater than the degree of the denominator. So if I want to solve this, probably the easiest way is to do long division. I can also do the well-chosen zero thing from the first section that we studied in this chapter. So here's a possibility for this one. Instead of doing long division, I'm going to do a well-chosen zero. So I leave the x cubed alone. And I really want this to cancel with the x squared minus 1 down here, and it can't because of the x cubed. So I'm going to write that differently. I'm going to write that as x to the first times x squared, and then I'm going to add and subtract something in the parentheses over here. X times x squared is x cubed, so this is completely equal to this. Now in order to make whatever I have here reduce with whatever I have down here, I need this to be an x squared minus 1. Well, that's legal. I can do that. I can just subtract 1 there as long as I also add 1 to compensate. It's just the well-chosen zero thing that we talked about at the very beginning of this chapter. So now I've got x times x squared minus 1 over x squared minus 1. And then if I distribute that x, I also have an x over x squared minus 1. And then these guys reduce, and I'm left with this. And I can factor that to x plus 1 times x minus 1. So I've got a basic rule for that, and then I can do partial fractions the traditional way over here. Now this is the same result that I would have gotten using long division if I didn't think of the well-chosen zero. But the idea is, if you have the degree of the numerator greater than or equal to the degree of the denominator, you've got to do something to write it as a quotient plus the remainder over to the divisor. And the well-chosen zero is just a shortcut that allows you to avoid the long division and get the same result. So if the degree of the numerator is greater than or equal to the degree of the denominator, go ahead and do this. Another possibility that could come up, that it didn't come up in any of our examples, but it could very well come up in your homework, is you might have a numerator and denominator that have a common factor. So here's an example where that might happen. Let's say you've got x minus 2 over x squared minus 5x plus 6. Now, if I don't look too closely at this, based on everything that we've talked about, I'm thinking I probably have to do partial fraction decomposition because I've got a polynomial in the numerator and a polynomial in the denominator. Basic rules don't work, and if I let u be the denominator, I get 2x minus 5, and I can't multiply 2x minus 5 by anything to get an x minus 2. So I might think to myself, I have to do partial fractions, but I don't have to. Watch what happens when I factor that denominator. I need two numbers that multiply to give me positive 6 that add to negative 5. Negative 2 and negative 3 will work. If you're not careful, you might keep doing partial fraction decomposition, but you see what happens, right? As long as x isn't equal to 2, I can reduce that with that. And what I really have is just this. Oops, minus. And that's easy. That's a log of the absolute value of x minus 3 plus c. So factor the numerator and denominator first. If there are any common factors, reduce them. If you do, it might turn out that you don't need to use partial fraction decomposition. It might be a basic rule. It might be a u sub. You just never know. So factor first. And then lastly, we haven't done any like this, but you might have one like this in your homework. Sometimes your u substitution will lead to a partial fraction decomposition. So maybe you've got something that looks like this. That looks complicated, but it's really not that bad, because the derivative of e to the x is what? Derivative of e to the x is e to the x. So this is actually really simple. That's du, and that's a u, and that's a u. So this is actually the integral of 3 over u plus 7 times u minus 1. And that I can solve with partial fraction decomposition. So sometimes you'll do a u sub first, and you'll see something like this, and then you'll do partial fractions and then back substitute. So even if it's not a polynomial over a polynomial, if after a u sub it's a polynomial over a polynomial, you can use partial fraction decomposition. Now, this last part is just a reminder of everything we talked about in those videos 2, 3, 4, and 5. If your denominator, after you've factored it, has linear factors only, and you take your original fraction and you write it as its partial fraction decomposition, you multiply by the LCD and you end up with this equation, and it's an equation involving your a, your b, your c, the numerator of this guy, and all of those factors that you canceled. If you only have linear factors in your decomposition, what you want to do is you want to set those factors equal to 0 and solve for x. So those are the x values that make those factors 0. They're also known as the roots of the linear factor. And you're going to substitute those into that equation. As you do that, almost all of the terms are going to cancel except for 1 or 2. You can use that reduced equation to find a, b, c, or whatever it is. Now, if you happen to have a repeated linear factor, that's not going to work. That's going to work for some of them, but it's not going to work for all of them. If you have repeated roots, let's say you had one root that was repeated, you're going to get all but one of your constants. If it was repeated twice, you're going to get all but 2 of your constants. You're going to have that problem because whenever you find the root of the linear factor and you substitute, a whole bunch of terms are going to cancel out. Instead of just one term canceling out, you're going to have 2 or 3 terms canceling out, depending on how many times that factor was repeated. If you have a repeated root, you're going to substitute other x values as necessary in order to find the values of the other constants. Now, I usually choose simple numbers like x equals 0 because polynomials are really easy to evaluate at 0. X equals 1, x equals negative 1. If those are already taken because they are the roots of my linear factors, I might try x equals 2 or x equals negative 2. But I try to stick to small integers just to make the arithmetic really easy for myself. And then remember, after you've done that, you're going to have an equation that involves almost all of your constants. You've got the values of most of them because of this first step. So you back substitute, and that's going to allow you to find the values of the other constants. Now, if you have irreducible quadratic factors in that denominator after you've factored it completely, we handle this a little differently. We take our equation and we multiply by the LCD, and then all the denominators cancel. So you're going to distribute on the left-hand side, and you're going to collect like terms in x. Then you're going to have a polynomial in x on one side and a polynomial in x on the other. The way we find the coefficients, a, b, c, d, however many coefficients we're looking for, is we set the coefficient of x to the n on the left-hand side equal to the coefficient of x to the n on the right-hand side. So the coefficient of x cubed on the left equals the coefficient of x cubed on the right. The coefficient of x squared on the left equals the coefficient of x squared on the right, and so on. The constant term equals the constant term. You're going to have the same number of equations as you have unknowns. So you might have 2 equations and 2 unknowns, 3 equations and 3 unknowns, 4 equations and 4 unknowns. It doesn't matter. You're going to have the right number of equations for the number of unknowns you have. Then solve that system of equations. Now, here is a point where you might have to review. You might need to review solving systems of equations. If you just look up solving systems of equations on YouTube, you can find lots of videos out there that will remind you how to solve systems of 2 equations and 2 unknowns, 3 equations and 3 unknowns, even 4 equations and 4 unknowns. And that's probably the largest number of equations and unknowns you would see in a partial fraction decomposition problem in our class. So those are your reminders. I guess there should be one more reminder. Remember how to state the decomposition. If you have a linear factor repeated n times, you're going to have a constant over that factor plus a constant over that factor squared, and you're going to keep going. You're going to have n terms. The last one's going to be a constant over that factor raised to the n. And then the last one, the last tip is if you have an irreducible quadratic factor. This is not factorable in the real number system. It's only factorable in the complex number system. You're going to have ax plus b over that factor plus cx plus d over that factor squared, and so on. You're going to keep going. Eventually you're going to end up with, I don't know what the letters are going to be, I'm just going to name some. A constant times x plus a constant over that irreducible quadratic to the nth power. If there are 3 of these, if this is cubed, you're going to have 3 terms. You're going to have this one, and this one. But the main difference is if it's an irreducible quadratic, you're going to have a linear expression in the numerator, and you're going to have that raised to the first power, the second power, all the way up to the nth power. If it's a linear factor, you're going to have a constant in the numerator. And in the denominator, you're going to have 1 term for each of these powers. So if that's cubed, we'd have a over the factor plus b over the factor squared plus c over the factor cubed. If it's cubed, we stop. If it's raised to the 4th, I go to d over the factor to the 4th. I always stop at whatever that power is right there. That's going to get us the partial fraction decomposition. And this that we talked about right here, this is going to allow you to find the values of a, b, and c. Then, of course, you back substitute and anti-differentiate. Thanks, guys. Thanks for your attention.